Evening, everybody. I must say, let's just start off with this. Nuclear physics or bad geophysics, how not to be fooled. All right? And this is a very interesting talk. This paper was presented about 3 years ago by Greg Hodges. Okay? And there's been quite a good follow-up on it. And I'm actually, when Sue mentioned it, could you use it? I said, I have no problem at all. Because I'm going to be spending tonight telling you about a pseudo AMT receiver, and I've been told quite clearly to take the M out of the AMT, and we'll call it the audio telluric receiver. All right? And if you go back to a paper by Helt in 1964, they were actually doing it then. All right? In Finland, they were actually doing it with a telluric, they're doing a pure telluric system over there. But nevertheless, let me start. And we got the introduction and all the rest of it. Right, so you got the audio magnetic telluric signal from 1 hertz to about 20 kilohertz. All right, it goes below 1 hertz, but we are interested in the audio side, so we are above 10 hertz. Origin spheric thunderstorms. All right. You've got 5 channels. If you're looking about the original layout, the recording of the pickup, the cycle, you've got 8 to 10 stations a day. Now that comes out of Alan Jones's electromagnetic manual, all right? And I've spoken to Neville. Neville says sometimes you can do about 12 stations a day. Not, huh? You can do 20, all right? The stratagem, which is a lot, huh? And you can do 20, so therefore, and again, normally there's post-processing and editing involved, right? There's not on-site. So just to put it into perspective, that you've got your HY, HZ, HX, and you've got your EY, and you've got your EX over there. You've got your 5 parameters that you're measuring. And so the source of the field, right, it's a plane EM wave perpendicular to the ground. All right. Let me start off right at the word, is that an email from Greg was saying that, 10 meter stations, you've got this big problem. But the field is perpendicular, all right? Perpendicular to the ground, all right? So whether you're 10 meters or 1,000 meters away, it's not going to make much of the difference except to the amplitude for the general system. Okay. Now, resistivities of different rocks and minerals. You've normally got your low resistivities in red and your high resistivities in blue. All right. It's just that these Chinese decided that they're going to invert everything. So when you're looking at these plots and so forth, remember, blue is low, red is high. All right? As opposed to the normal, where you're having your low resistivities in red and your high resistivities in blue. There we're looking at 1 hertz, 10 hertz, 100, 1,000, 10,000. Okay. So you have a logarithmic scale. That what you wanted to see? Yeah. This Fong Kong, all right, Cas Lotte gave it the name of the Fong Kong. But it's actually called PQWT, basic principles, all right? The source can be regarded as a plane wave, and that is just Cagnat's resistivity, Cagnat's AC resistivity formula that he's using over there. And they're using a penetration depth of 503. Cas has come back to me and he's using the CSAMT one of 356 with a lot, and his results have been a lot better. He's bought the top of the range one that we can actually put in the different frequencies, whereas these smaller ones, you don't have a control on the frequencies that they are looking at. All right? Now, here's the PQWT premise. Because the magnetic field component is basically stable in most scenarios, small in the area of measurement, it will be regarded as a constant function of the EX response. All right? Now, this is where the wheels fall off and the violations come in and these type of things. All right? Yes, it is a violation of the rule. All right? We all understand that. But let's just stay with this problem that the rule has been violated at this point. But let's see what the data what data comes out with this violation involved.
What units are the data in?
The data, the units, they are in millivolts. They are clearly in millivolts. They're not in ohm meters because it's a relative measurement, and they are quite. I spoke to the Chinese about this. Remember, I'm having a problem with the Chinese. I made the big mistake. We had a teleconference with 4 of their guys and myself, and I said that you've got a patent on this, right? So you've got proprietary information. This information that you have is proprietary. You can let me know because we can't do anything with it. And there was a silence. And they said, what does proprietary mean? So I explained to them. And for the rest of that conversation, for the 3/4 of an hour, every time I ask a question, it's proprietary. It's proprietary. So I haven't been very successful in getting through to the Chinese and finding out exactly what's going for what. Is that we got the big system, and Cos and I, we got the frequencies out of them. So Cos can now do a telluric measurement on his own frequencies. So he can go and calculate out, and he can decide what's going for what. But nevertheless, let's just carry on and stay with this premise for the time being. If you look at the spectra, there's the 1000 Hertz spectra, all right? Now, this comes straight from Mike Jones's electromagnetic course notes. You need to measure H to 0.5 times 10 to the 6 nanotesla. All right? That's very, very small. You can record tellurics during the daytime, but not magnetics very accurately. When I look at the Phoenix and the Zonk system, they have a calculation where they actually do Hx over Ey. And then what really happens over there, Ex over Hy. And what really happens over there, they have a thing called coherency. If there's a coherency problem, they actually put the figure in brackets because the standard deviations and everything is just too far apart. They can't. They're not happy with that data, so therefore that data has to be flagged as suspect. Okay, but when you're going to have a look at this comes up. You can actually see that there from. It might be a bit small for you at the top over there, but at the bottom over there, you're from 1600 hours through to 1600 hours, 4 o'clock in the afternoon to 4 o'clock in the next afternoon. So you can actually see what's happening to EY. And then you're going to have a look. You're going to have a look at HX. Much of a muchness, but there's a change. Yeah. It looks like the ratios are changing, but the general trend is very much the same. Okay? So maybe there is something. What I did, I have a Spectral Mag. I've got a Bartington magnetometer, and I can go and collect data at 100 microseconds. I was collecting data, 100 microsecond samples, 20,000 samples, average of 10 stacks. And then I did the Fourier transform on the data. And, all right, I removed the 50 hertz because I did this test at Geotron. All these tests, it's in my backyard. So you're talking about Jan, we're talking about noise. I mean, how noisy do you want to be? I'm in an industrial area. And that is what it's looking like. But you're looking at, and this is calibrated, okay? You're looking at signals of about, there at 10 hertz, you're looking at about 0.2 nanotesla. There at 100 hertz, you're looking at about 0.1 nanotesla. You're going up over there, above 100 hertz, you're going over there 0.05 nanotesla, 0.03 nanotesla. So you're looking at about 30 picotesla. 30 to 50 picotesla. That's a very small signal that you're looking at. Okay? That's at a 10 meter. All right? I have not done it yet, but I still want to do it. I want to go and take it to the field. When I got this lot going, it's a lot of times you have equipment in your store that you don't even realize that you've got. You've got the fancy equipment, but you haven't really learned how to use it in the last 20 years. But be that as it may, I would love to go and do a 10 meter, 100 meter, and 100 meter spacing of the same type of thing in the field where there is not noise, to see what response comes out over there. Nevertheless, let's carry on. Also out from Jones's work, you could have a look at the diurnal variations and so forth. Okay? Now, the nice thing about Cagney's formula is that whether you do it in the mornings, you can actually see there, from 8 o'clock in the morning, she's nice and quiet, all right? 12 o'clock, after 12 o'clock she starts building up again over there, and you can see that she's getting quite noisy nocturnally, all right? So the actual idea is to keep your readings in the morning, and they're relatively clean and stable, and you're going to be having less noise available to you. But the ratios are still the same. The fact that you've got a ratio does not matter whether you're doing a survey in the morning, whether you're doing a survey in the afternoon, you're looking at a ratio. Okay?
But
So,
in
yes.
your instrument, you don't have a ratio. So
What I've heard from the Chinese is that that constant is not a fixed constant, it's a constant of the frequency and the response.
I'm not worried about that, but I know from practical experience that your telluric just change during the day.
Yes, she does.
Yeah.
Well, you can actually see there quite considerably. There is quite a change.
So the whole point is, if you're not leapfrogging along a profile, then you're going to get shifts.
Yes, you're going to get shifts, but again, you've got a baseline, all right, and you've got a diurnal shift in the magnetometer. What do? You have the magnetometer base station running. If you really want to go and have a look at that to that extent, right?
Yeah. I'll talk to you afterwards about that.
It's again, a lot of times the base station is a prerequisite of a survey. You go to the survey area and you find that the diurnal variation for the day is about 7 nanotesla for the time of your survey. So you really want to think to yourself, did you really need a base station? Yes, you needed a base station to find out that it was only 7 nanotesla. All right? But if you did not have a base station, you would not have degraded your signal, your data by very much. To answer Jeff's question about the spectre 2 times of the day, there's a spectre also out of Jones's one. 4 o'clock in the morning, you can actually see how noisy it is, all right? Then we're looking at 5 o'clock in the afternoon, you can see how much quieter it is. It's a big difference over there. But there's one of the few cases where I've got HY and EX plotted on the same plot, all right? Not just the impedance, all right? What that Phoenix and Zong do. They just display your impedance coefficient. So what I did yesterday at 11 o'clock in the day, I went and did, all right, now the Geotron test site is in my backyard. It's as simple as that. How much noisier can you get? But the thing is that at least I can go there at any time. What is very interesting, I don't have a slide of it. I heard them shunting, all right, with the electrical train and shunting. And then I went and started a measurement, and it was incredible. When I heard them start shunting, you just see the signal go completely haywire, but really completely haywire. Again, so having said that, I went and did a reading at 11 o'clock in the morning and 11 o'clock at night. And you can actually see the bottom slide over there. You can see I've added, just so that it is quite clear, you couldn't read 0, 15, that's millivolts by the way, 30 millivolts, 37 millivolts, they're the 2 scales, all right, just to show you. What happens with this instrument, they auto-scale and they remember that you're taking a reading in the field. 3 seconds after you finished your survey, you've got a plot like this. That says a lot. There's not much equipment that can give you those answers as quickly as that. Right, resistive amplitude frequency defined, constant, can work if. Right, there comes the big ifs. All right, you assume you're in a 1D modeled Earth, and the principal impedances are equal. Okay, the ground is horizontally laid, the media homogeneous and isotropic. You have to ignore the displacement current effect, that coherency problem, and do not consider EX and HY between the pi over 4 phase angle, data collection lines should be perpendicular to the structure. Because if they oblique to the structure, you can really get some fancy things. But that's an AMT problem, which Jan will reinforce over there. Both Zong and Phoenix calculate the display the characteristic impedance without displaying the actual E, X and HY values. This is to be confirmed. But I think I am correct there. Richard Day says it is so. Okay? Measurements with unacceptable coherency between the electric field, EX, and the magnetic field are normally highlighted in the plots. Incoming electric field intensities typically are microvolts levels with magnetic field intensities in picotesla. Now we come to the interesting part. Modern electronics and part of the PQWT patent revolves around signal enhancement. I just want to go back. All right, they hide behind their patents. All right. But one thing I do know, I know a little bit about electronics. And when I saw this, and I said, holy moly, this is true. And this is even Louis there at Spectrum, right, can take cognizance of this. That you're starting life with an analog signal. The geophysical fraternities in the 70s did everything in their power to try and do an A to D conversion as quickly as possible. And that's utter bullshit. That is utter bullshit with the electronics that you have today, in the 21st century. Because remember, all these arguments, a lot of this paper, I haven't seen a new paper on AMT equipment, per se, since Zong's paper in 1972. So, all things being equal, there's been no improvement on the electronics per se. Now, their patent that they've been playing around with, and this is what it comes down to, and this is so interesting. They have the detection probe, they have a detector probe interface, then they have a radio frequency filter, then they have a preamplifier, and they're going to the differential. Now, this is electronics, but they immediately go to the differential mode. So when you're enhancing a signal, and you've got a balanced signal, all right? Any random noise that is not balanced on the signal gets kicked out, all right? And that's...
What do you mean by a balanced signal?
What do you mean by balance?
You've got a differential signal, all right? You're looking at the differential signal, all right? Now, if there is some noise on the negative line, all right, and it's not present on the positive line, she'll kick it out. All right, you've got a bandpass filter over there that you analog electronics can do that, and modern there's a lot of papers that there's a book that I get. It's called Vector, where they talk about analog electronics really coming to the fore again, because they're realizing that you can kick out noise easier these days with modern analog electronics than what you can do in going into the frequency domain, all right? Going into the frequency domain and trying to clean it over there mathematically.
My ignorance, but I don't see why the signal has to be differentiated.
We're coming back to this. Let me finish over here. So you've got a high-pass traps, you've got your first low-pass filter, you've got a level magnification. Second low-pass filter, high-pass filter. Let's carry on. And you've got A to D sampling. Right, now let us just say what they are doing over here. They are taking the signal. Now previously, you were collecting that signal and you're doing a Fourier transform and then you're looking at the frequencies. They're not doing that. They're looking at the AC signal. They're looking at 56 hertz signal in the analog domain. Alright? And they are measuring that, the amplitude of that signal at 56 hertz. They have a very, very tight Q. So it's 56 hertz plus minus 2 hertz. Alright? So you've got a very tight Q. So they're measuring it in the analog domain. Alright? And remember, the small unit has got 4 parallel readers. The bigger ones have got 8 parallel readers. You're talking about how can this measurement happen so quickly? Alright? How can this measurement happen in 2-3 minutes where the other systems have to be sitting for 20 minutes? But they're looking for that signal, and they're looking for that signal, and they're looking for that signal, and if they got the signal over there, all right, and it is 5 times the noise, the noise amplitude. Grab it. Take that signal.
You haven't told me yet why you have to differentiate the signal. I thought differentiation, if I understand differentiation correctly,
Yes.
will add noise.
If you take a differentiation,
Yeah, what are we differentiating with respect to?
all right. If you take a gate, the electronic gate, and you have an AND gate, A plus B is equal to B. All right. If you take an AND
Oh,
gate,
you mean we're differentiating between signals, we're not actually differentiating the signals.
yeah.
Ah, okay.
So then we've got this data processing unit. Now what is happening over there? You've got that A to D sampling, and somebody made a comment, oh, it's a 12-bit or it's a 16-bit A to D. Who gives a shit? You know, these people that want 24-bit, you know, or 23.5-bit floating because you've got a minus sign available there to you, it's all fine and dandy. But then you 24-bitting noise as well, by the way. Yeah, just take cognizance of that. Right? So in other words, put in a clean signal. There's a nice discussion, if I may, with Jan. Jan is saying he's got a wonderful instrument, and starter gem is a very nice instrument. But can't he clean up the sensor noise? You know, can't he get some, you know, just that LC, lengthen that LC at the moment. Those starter gem sensors have an LC of about 1 or 2 seconds. And if you can lengthen it to about 3 or 4 seconds, his signal to noise ratio improves. You know, it's little things like that. Right? And funny enough, it's in the analog domain. Louis has the same problem. Here is the toy. The Hong Kong. Right, let's just go. Its accuracy is 1 microvolt. Right? You've got different depths and so forth and so more. All right. Now, the discussion. HI field is small and stable. Using a constant will result in faulty readings only on complex structures. If the assumptions are met, good data can be obtained. Don't forget, $2,500 as against $50,000 or $60,000 for a full AMT set. Groundwater exploration normally requires a lower level of precision to make an interpretation. Now, please take cognizance of that. There's a mag traverse over there. You have this dike over there. This is in the Transvaal series. And at position 9, a hole was drilled, all right, and picked up lovely water sitting over there at about 110 meters, all right. What I can say, we have seen this, and Cos has reinforced it, is that you can take these figures on the left, which is the depth. These are just your station numbers. Now, the actual method of operation. You have your electrodes put into the ground 10 meters apart. And then you'll be jumping 5 meters, or 2 meters. You don't want to go and jump 10 meters, it's just, they say it's not a good idea. But horses for courses. And if you go and take a mag survey, you want to do 5 meters or 10 meters survey. I'm talking about groundwater now. All right, let's just go back, leave exploration out for the time being, groundwater. What has happened is that on plots, on small plots over there, where you've not been able to, this has been in the field, you've got nice mag data, but you have not been able to get resistivity because you have to have your electrodes too far apart, and incidentally, to do a sounding, to do a resistivity sounding with not a Lund system or the multi-electrode system will take you about an hour and a half to do a sounding to 300 meters, whereas this system it takes 3 minutes. Big difference. Big difference. And you can go and do a profile. So there's the profile. Let's just take the next one. Yes?
Can you just say at what depth was the water strike with it? I'm sure it was not at 120 meters.
No. That particular hole, the water strike was down to about 40 meters. All right. Through the bed.
At 40 meters, there was nothing visible there.
There's nothing showing there at 40 meters, but they hit water at 40 meters. And the owner said, "Any water?" And I said, "Bullshit, carry on drilling," because the actual thing that was showing me, and I multiplied it by 0.7. I'm going to come back to that one. And I multiplied it by 0.7. You're going to take 90 times 0.7. They're looking at about 68, something like that. All right? And I said, "Carry on drilling. I want you to go and drill. All right? I want you to go and drill over there to 80 meters at least." All right? And in the end, when he started getting more water, he went down to 110. And it was difficult getting him to convince him that he's got to go and do that.
Dike was vertical or horizontal?
What?
Dike here was vertical or horizontal?
Yes. Yes.
Vertical.
Yes. Yes. You can see from the mag. Again, a problem. Mag lines run too short. Too short a mag line. You can't do interpretation of that mag data because you can't get your zero line out of that data. Yeah, but that's an age-old problem.
No, right. I disagree with you. I would have had to pick a border, the position on that mag data. I would have picked it between 8 and 9.
Between 8 and 9.
Yeah.
Well, that's he drilled at 9.
So,
Yeah. Okay.
so
So that's Sama saying, eh?
What is the x-axis on that?
What is there?
How long is the?
Multiply by 5. Multiply by 5, so that's 35. So that's 35, 36. It's 180.
What were the chips? Were they Dollar?
Transvaal series. Transvaal series was shale.
Is the mag from the shale or from the dike down?
No, the mag's on the dike.
Well, that's really right on the edge of the dike.
Yeah.
Yeah.
Here was, let me just jump 3 slides. You can actually see there, I should have made the slide larger, is that the drill, it was drilled over there. But you can see the geology sitting over there, and you can see this it's almost a magnetic shale sitting over there, coming around over there. But the geology says it's been covered by the surface geology over there. And then if we come back to it, this is a hole that was already drilled. All right. So we had the hole sitting over here. All right. We have north going up, and then I did a traverse over there, and I did a traverse over there. It's 25 meters away from the hole, on the eastern side and the western side of the hole, just to find out. All right. The hole was drilled on position 8. All right. The hole was drilled over there on position 8. All right. And this is on the west side from north to south, from minus 20 to 50. And that is from the eastern side, from south to north. And the corresponding hole would be on 0.7 over there. So you can actually see what is happening, that the whole structure was clearly delineated. This was early days because I was trying to find a hole with water, and we knew that there was this magnetic shale was, it was right on the edge of the magnetic shale because the magnetometer data showed it, right? And this was one of those ground truthing things. Go to an area that you know to find out what the response of the instrument is.
Can I just ask something else?
Yes.
Just go back to that. Yeah. So, going by previous pattern recognition level, I would have said that 9 would have made a better hole than 7.
Could be. But the only thing is that, remember, 7 it was drilled already.
Okay.
I went to this area after the hole was drilled. Because a local geologist went and...
And how good was 7? What was the yield?
Very good. It was an oak cattle. 15 days in calendar year. Divided by...
That's a fair.
Yeah, that was reasonable.
And what was the depth of the hole?
Yeah, what was the depth of the hole?
85 meters.
85.
85. He drilled to 85.
Just hang on before you.
All right, let me show you 85 on here on the 1-to-1 on the 1 scale. Sorry, there is 85.
Yeah. Okay.
All right, but if you multiply that by that 0.7,
Yeah.
okay, she would actually take her down to about there. The 85 meters I'm talking about now. East of Francistown, Hansi quartzites with a lot of disseminated copper mineralization. All right. So the first on the top over there, we've got a maximum. All right. We've got the maximum response over there, and the arrows. Unfortunately, I've been trying to get, but I mean, these guys went to the field, and I said, "Shit, could you not given me a longer line?" I said, "Yeah, you can. Just give us 8,000 puller and we can go back to the site to remobilize to Francistown." But the area that I'm interested in is just this first 130 meters. All right? And there's the conductivity. This is the EM34. Run over it as well. And there's the magnetic profile. You can actually see there's not very much over there. If you can't read it, you're looking at 660 to 800. So you're looking at 140 nanotesla full scale. EM34 was 20 meters and the maximum was also 20 meters.
Okay.
You can actually see the maximum scale over there. The voltage, if you can't read it, we're looking at a maximum voltage over there of 8.39. So it's a very, very small signal. And remember the other data, we're looking at 37 millivolts. Right? Yeah, we're looking at about 8 millivolts sitting over there. Okay?
Remind me again, what's the coal spacing on the...
This is 5 meter spacing over here. So there's 0, 50, 100, 130 meters.
The coal spacing.
The what?
The coil spacing.
Oh, it was on 100 meters. It was on 100 meters. The maximum was on 100 meters, and the EM34 was on its... it was a vertical dipole on 40 meters. They went and drilled on 15. Okay? And they had drilled 6 dry boreholes, and they drilled a hole over here, and they drilled 2.5 liters. 2.5 liters a second or something like that. Something equivalent to about just over 1,000 gallons an hour. Alright? That type of thing. Not very good yield, but in die land van niks is die een oogkoel. Alright, unfortunately Cas was supposed to be here, and of course he is very enthusiastic about the Fong-Tong. Natural frequency electric log resistivity, that's what he calls it. Alright? Calibration natural field EX sounding at a borehole SD20 using the 1000 meter depth setting on WT 1500. The indicated depths are 0.3 times the skin depth. Black line is the median value of the 5 repeat readings. Right? That's the type of fit that he got in over there on for this borehole. All right.
What was the thickness of the Kalahari?
Hang on a second. Are you talking about the Francistown one?
This one, yeah.
This one? I don't know.
Go back to previous line. Was that east of Francistown?
No. This is a new one. Kaslotter is a complete.
No, go back to those Max Moon and absolutely true.
Almost a quark, isn't it?
Well, the problem that I have, Jeff, is that I've only got so much of Fong Tong. I've only got 130 meters of Fong Tong. Although they did just under 1200 over there, just under.
Yeah, I accept that, but the EM34 definitely is not going to go to the kind of depths.
No.
And the maximum probably not.
The Maxman would have got through to it. Because if you take those. This area over here, I know, is about 40 kilometers east of Salibi Piqui, actually, not Francistown. Okay.
Oh, I don't doubt there's conductive stuff around in that, but it's not very conductive. It's 200 ohms according to those conductivity. And the depths, if your Kalahari is 50 meters or more, then the traditional frequency domain stuff.
The Kalahari is not that thick. Not that thick in that area. Actually, there's very little Kalahari because you're going into the Karoo there.
Okay, fair enough.
You're out of the Kalahari because you're out of the Kalahari into the Karoo. I'm just looking at the geological map in my head, which is not very thick.
Well, in fact, you're at okay, I leave the topic, so from the traditional frequency domain, you're picking up shallow targets.
Yes.
We turn our eyes down to the Fukong.
And you're looking at a slightly deeper target.
Well,
You're actually getting through those shallow targets.
But we're not seeing the shallow targets.
You're seeing through those shallow targets.
So that all blue is feed to the frequency, that all blue,
Yes.
very blue.
Blue is
They
low.
Not feed to the frequency domain, no? Anomalies. Are they different?
These are not frequency domain.
No, you showed before frequency domain, is what I mean.
Yes.
So they not feed each other.
Yes, because
I'm very satisfied. I don't like frequency domain.
if you go and have a look, but they don't want to tell me, but it looks like they go from about 25 hertz up to about 8,300 hertz. Right? In a logarithmic scale. And I don't have it here, but CUS, when we pulled out the frequencies, because CUS's machine, you can actually you can have what they call a custom, and you can actually import, you can key in the frequencies that you want to go and check yourself. You can go and check those frequencies over there. And CUS's overlap very much with their frequencies. So what they're doing, they're looking at a given frequency, they have a very sharp cube, all right, and they're measuring that voltage. That's what they're doing. Right? They're not going into the frequency domain and pulling it out digitally. They're actually pulling it out in the analog domain. All right. Yes, he did a resistivity sounding down to 168 meters over there. There's the targeted to the MFG. There we are there. Intensely sheared hornfelds, and that's where you drill the hole. Yield 50,000 liters per hour.
But why doesn't he give us to us in seconds? Because that is the norm.
Ach man, I still think in gallons per hour. Yeah.
Right. Every geohydrologist talks talks about meters per second.
Well, fortunately, you're not a geohydrologist, neither am I, and neither is CUS.
Yeah, but I would like to...
And I'm older than you, so I talk about gallons per hour. But yes, there should be a standardization. But the standardization is liters per second. The standardization is liters per second. But it gets very, very difficult. And if you take it, it's the same. Petrol consumption was gallons. How many miles per gallon? All right. Then they converted it, and it's liters per 100 kilometers. What a stupid bloody thing. And it's the same way, liters per second is not a very nice term, but it is the standard.
But if I do my pattern recognition again and ever, why did he drill the hole there and...
Ek weet nie, hy sou hier so gewees het om self te antwoord.
Yeah.
Jammer. I would have loved to have been, that it would be here.
Because on the resistivity, there is no indication of a good position for a particular hole.
No.
I would have put something down. I can't read the numbers, whatever, but where
I'll read the numbers for you.
the resistive.
I can't read the numbers either.
Don't worry. Don't worry. You could have had 100,000.
There was just a closer one of it over there. All right. What did he do here?
Very Asian.
Oh, hang on a second. This was in Iran.
Yes, exactly, very Asian.
This was in Iran.
Yes.
This was in Iran, down to 900 meters. All right. And is that, unfortunately, I could say it because Kas said he would be here to explain his slides. All right. Detailed section, 200 meters approximately after severe. The noise in the right section probably caused by a combination of high contact resistance. Oh, you can. High contact resistance and frozen water in the fault zone. Okay? Right. Ek gaan so 'n bietjie sit en 'n bietjie wyn kry. No, it's Edgar.
Okay, if you guys want me to explain what's going on there, we did a test with another sort of electrophysical technique, which is called the LOSAR radar there. And at the same time, we got Ray River to repeat with his Fong Dong, because if you've got electrophysics multiplied by electrophysics whatever, then perhaps you can get a good answer out of that whatever. So at the top, well, go to the left whatever, and the red material there is a pebble deposit on the farm. Maple Laughter is very well known for his diamond content whatever. The green stippled boundaries whatever, that's a dike which goes through there whatever. So the old patio, the rivers that they followed in a way, they followed as a dike, and you are also very near the contact between the information in the Dolomite to the north and the Monte Cristo information to the south. Now there is an access road to the famous Pinos pothole. The Pinos pothole at its heyday delivered 700,000 carats of diamonds or whatever. So it is of
Actually, the pothole is there. The pothole is about here.
I wanted to see what the radar does, and Ray wanted to see what the Fong Dong does, or whatever. What's it called?
Not Poyong Tong, Fong Kong.
So above
Wat lag jy?
is the LOSAR radar, and lo and behold, well, I haven't seen the raw data, I was just presented with this color picture and a huge report in Russian. And although I can talk the Russisch fluently or whatever, I could not really, well, I don't have the time yet to read the report. So, but the upper picture, I think, shows us the tip of the red stuff, which is the gravel, and then below it is the duck. Okay. Then raise some Pierre with the Tom Fong the measurements, whatever. And I want you to see whether that it's an excellent dolomite detected, because the blue material on the laser and the radar, that is, I think, the resistor whatever, and the black and blue stuff is conductive. So, yes, the Tom Fong whatever, it could determine, oh no, yeah, that's correct. No. The blue stuff is conductive whatever, and the dolomite is the resistive. So I think in the first instance whatever, that its depth, the indicated depth is wrong, because it would indicate whatever that you have a conductor again below the solid dolomite, which I don't think is true. And then the ray came again whatever, or not ray, he said his son again whatever, and they repeated the reading whatever, and they got exactly the same image, except that the depths are much more shallow, and they are much more in line with the radar. And the picture at the bottom is what I expected to see. Now, this whole technique to me is just a telluric measurement technique, whatever, and as anybody who attended my geophysics EM lectures will know, whatever, you cannot determine depth out of telluric information. All you can determine is the resistivity or conductivity. If you want to have a depth to your target, you need to have the magnetic component. Okay, and that illustrates it beautifully, I think, whatever. The depth control is a bit wacky on the telluric measurements, whatever, but yes, if it can indicate a conductor amongst the resistors, whatever, then yeah, why not? Okay, right.
Thank you. Couple of things.
A percentage of your salesman.
Let's just take the middle one over here. She's down to a depth of 150 meters. All right. Now, there's one thing that you need to understand. These plots that have been put out over here. All right. These plots that are put out over here is the data as it comes out of the machine. She's automatic scales, right? Remember, there's an automatic scaling. And just to come back to that automatic scaling to show you, I didn't show anybody, but I want to. You can actually see over there you go on to 37, but you're going to have a look at these lines where they've done, because of the automatic scaling, because this is actually a screen plot. This is a screen plot of what comes on the display. So you've got no control on the top and the bottom. There's a process, all that it is, she just kicks out the highest and the lowest reading, and she replots it. So you have to take cognizance of that. Now, this data falls into Surfer very easily. Then you can go and put things into a better perspective. All right. So therefore, coming back to this, I just want to show I'm not making any excuses whatsoever. I think this is a lacquer plot. That's excuses. Now, to support this whole thing about this depth calculation, all right, in the skin depth calculation that Edgar was talking about, that you need an accurate HY, all right, is that you can actually see there, it put it down at about 40 meters over there. Now, this is the 1 meter, this is 2 different meters, by the way. There were 2 different meters. This one is down, calibrated to 150 meters. She has 33 readings to 150 meters. Okay? So therefore you have a reading every 4.6 meters. Okay? This other one, this 50 meter one, gives you 30 readings. So you're looking at having a reading every 2.5 meters. Alright? So you've got there's 30 frequencies on this data, and there's 33 frequencies on that set of data in the vertical scale, in the depth scale over there. Remember, they are taking that frequency, they're taking the high frequency is your shallow, your low frequencies is the deeper stuff. Alright? So now you have a look at those two. You can draw a line here at 50 meters. If I draw a line there at 50 meters, I don't see that so clearly. But remembering this whole thing about this automatic scaling. But put it into Surfer and you can go and standardize your scaling, and you can go and compare that one with that one far better. Okay? I just wanted to add on that. Edgar? You happy?
Sorry, that's about you look as though you've applied a migration algorithm. You can't argue your way out.
No. I'm not arguing myself out of anything. I'm just showing you what I've received, the data that I've collected. I have not manipulated any data.
No, well, I'm not saying you have, but I am saying, surely the point of showing that is that the voltages are not constant over time.
Yeah, and I'm also reinforcing what Edgar is saying over there, is that with a depth, a conversion of the frequency to depth, all right, you really need an accurate HY. That's correct. And that actually manifests itself over here, because you can't really see that. I'm still alluding is that she's been automatic scale. I have not taken this data. Every bit of data that I've got, that I've showed over here, you're going to have the raw data. Ek het nie 'n probleem.
It shows the reason why we spend the extra $47,500 so we can get it.
Yeah, but you'd never found, nobody in the groundwater business has got that type of money to go and buy that equipment to go and find groundwater.
Yeah, I know.
All right, this is a groundwater tool. This is not a mineral exploration tool.
No, it's a bump detector.
It's a bump detector.
And there is a place
It's a
for
fucking good bump detector.
Well, I'm sure it finds good home with groundwater.
Yeah. But, alright, is it potkak? Is it bullshit baffled brains or something? But nevertheless. Right, there's some questions that came up. And why are the 2 component electrodes? Is it just easier for placement of the electrodes into the ground? Copper, that is chrome, stainless steel would have been more appropriate. Answer, it is purely design. You have your 10-meter cable, and you have your electrodes. I don't know why this was raised by the science school, by the Pseudo science school. And Now putting that into the ground is a damn sight easier, pulling that out of the ground, a damn sight easier than the old, a 16mm stainless steel rod. And you're trying to make a decent connection. It's purely design. So there was nothing fancy about this. And the Chinese have translated grass as yellow copper. Just by the way. It's purely design. There is what appears to be a magnetic choke on the electronic cable. Somehow powering that. I mean, if somebody just asked me that, is that... this piece of wood is a Geotron edition, for the simple reason is that if you don't do it like this, you can't get it into the cave. It's just where the two cables come together, and you have one cable into the connector into the machine. They just simply asked that question over there, that would have been answered. It's just a rugged connector for the cables. Reading time is too low. 1 to 3 minutes is not sufficient for reading the telluric field at any time, especially during the daylight hours. A minimum time for any device acquiring AMT data is accepted as a minimum of 20 minutes reading period under optimum conditions. Yes, I agree with you wholeheartedly with 1970s electronics. I rest my case. Yeah, don't even argue that point. Based on what premise? Published papers and the equipment was late early 90s. Electronics have improved greatly. All right. See the slide on the patent.
Ray, can you put the lid down?
Oh, my apologies. The depth estimate for the 1D section using a 10-meter dipole is completely unreasonable. Error in the formula or not. Skinner formula can be applied to the 1D field, and this is what the electromagnetic manual from what Alan Jones's notes say, all right, as it is perpendicular, whether it is 10 meters or 1,000 meters. If the two electrodes are 10 meters or 1,000 meters, it's essentially perpendicular. So you're not going to have the resolution, all right? Let's go wider. If you want a wider area, do a 20-meter separation, all right, if that really bothers you. What has happened over there, the Chinese did their homework and they saw, but hang on a second, cost effectiveness, all things being equal, 10 meter does it. And the data that we're getting out at 10 meter is reasonable. Okay? Yes?
Look, the separation between the electrodes in empty, you judge whatever the distance that you wanted, the separation, whatever, so that you don't bump your.
I quite clearly in my quick start manual is that you do not do this measurement without a tape measure.
Yeah.
You and if you have uneven ground, all right, I almost want to say apply the tandem, but that's not normally the case. But I do say quite clearly is that be consistent on your 10 meters.
Yeah.
So at least you're reducing your potential errors. You know, there are so many potential errors.
Yeah.
So at least if you can have a handle on them, do that.
What percentage of the skin depth is applied? What you're taking the skin depth, which actually always greatly overstates the depth of penetration.
Yes, it's 503 times the square root of, but CSANT uses 356. That's where I got this 0.7, where COS also uses this 0.7, and sometimes if you really have a conductive upper burden over there, you can actually go down to 0.5. What is the frequency being recorded? ranges from 8 Hz to 8,300 Hz. Note that Zong and Phoenix collected data methods. Collection method is 100-second slices and fed straight into the ATD converter. Thereafter, they do a Fourier transform. All right. PQWT stay in the analog domain until the signal at the selected frequency is measured, then only into an ATD converter. All right. There was another question that was put by that school over there. They talk about resistivity. So if you assume the numbers in the color bar in ohm meters, they are not in ohm meters. All right? Everything is very resistive. No, the values are not in ohm meters, but simply in millivolts. E. Volts per meter is the electric field. The practical units are millivolts per kilometer. Okay? For the magnetization field, B in the magnetic field intensity or magnetization field H we have. B is micron OH, where micron OH 4 times pi times 10 to the minus 7, and the practical unit is gamma or nanotesla. Posing these practical units of E and H to the Cagnon resistivity equation, E is much larger than H. What are the range of these values? I don't know the answer. And coming back, I was talking to Stephanie, is that yes, this thing has got lots of holes in it, right? But can somebody, and I've not found any published data. Zong, Neville Brown, said he spoke to Zong, they can't really give him. Right? Is that I want to know, I want to have a sound, a survey, and I want to see those values. And I want to do my own impedance characterization, right? And I actually want to run through some statistics with those numbers in how correct are the Chinese in saying that they, are they being presumptuous? Or they're taking a chance? Or have they got something going that they can use? They don't have to measure the magnetic field. They can use a frequency determined constant. Yeah? What have they done? We don't know.
Keller and Frischnecht, 1967, described the first of the telluric units that you can work with.
Yeah.
And despite what Edgar's just said, I think they believe with bimodelly, you can actually get a depth converter. I can't argue with that.
Excellent copy. I am Little Red Riding Hood in that discussion.
Let me answer Jeff there, whatever. He maybe that what Keller and Frischnecht, whatever, are a bit late in the game, whatever. There was first there was a Russian called Mark Danichevsky, whatever, which there I will confirm. He published a lot on the lyrics, but the actual book I wanted to get hold of was just written on the lyrics. It was by Professor Thirstendorfer or whatever, who was a East German or whatever, and his book on MT is you can get hold of whatever, but it seems like the book on the lyrics or whatever is not so easy to get hold of whatever. So I'm trying to get Detlef to see if we can get a copy of that from the German Geological Survey library. Okay, so then perhaps Jeff, we can answer.
If you want, they can find Danichevsky 1960 something, 5, 6, about.
No, I'd agree the Russians were the first to look at it.
It's not the fields, there are 7 and 10 actually, but book was in 60 something.
Yeah, but Jeff, I want to say to you, if it was easy to get the reliable depths out of just the lyrics, why do we go to the trouble of doing the meta-lyrics?
Well, that's free lunch thing again, Andrew. But I take it we're on the same side. We believe what we're looking at here is a caloric unit which is running on caloric voltages.
Yes.
And that's
No,
it.
nothing wrong with that.
No, nobody's saying there is.
Relation is accuracy, really. No? Accuracy. Only caloric measurements.
I and the Chinese must take the M out of the system.
Yes. Yes. Yes, please. Yeah. I got the dragon or scorpion. Kick ass.
It was any consolation, quite interesting. I had an email from Bill Peters. I don't know, you know Bill Peters?
Yes.
Ah, in Australia, all right? Been around, I mean, he's almost as old as Jeff. And sorry, Jeff. But it's only Eddie that's the senior partner over here. And, but he says, this Fong Tong, you know, that you talk about and so forth. I want to know more about it, because it's actually the guys in Australia. There are some guys here in Australia propagating this thing as well. You know, and he's now very keen. So, I mean, somewhere along the line, something is happening. All right? But again, yes, it has its faults. Edgar is quite correct. It's a telluric system. All right? It's a telluric system, and it's a large using the your skin depth formula to go and try and determine depths, all right, from the resistivity and the frequency that has been determined. Yes, you can get into trouble. But the data that I've shown you tonight, put it this way, you've never seen that data out of electrokinetics, have you? Never seen that data, such data out of electrokinetics. You've never seen such data out of ADROC.
I see red herrings on the horizon.
Fortunately, I don't do any work close to the coast, so we leave the herrings out of it. But Irish spot case, you can hit me with buttons and whatever the case may be. But again, Sue would like, especially the students over there, go and look at that form, all right? Apply your mind. And there are 5 questions over there. You have to apply your mind to those questions. It's not a matter of just a cursory glance over this paper and saying, monkey puzzle, let's fill it in. And I would actually say, it shouldn't be filled in tonight. It shouldn't be filled in now. It's a bit unfair, because nobody's applied their mind, because they've all been drinking like you.
No one's been drinking like you.
Well, they're just asking how we work.
Okay. I'm going to call it there.
Yeah.
Thank you very much, Ray. Have we exhausted our list of questions at this stage?
Yeah.
Fine. David, hit us. What's the page? No, are there any mineral applications to this? Can you map depth to bedrock or
Map it.
Or, okay. Can you at least full stop map this the surface of a soil bedrock interface?
Geotron test site. Geotron test site, we've got clays and so forth. Then we're going into weathered anesthetic lavas. I'm just going to do this over here. Put it over here. Is that we just got clays and so forth. There at 48 meters, we're going into time ball shales. All right? There at 68 meters, we're going out of the time ball shales and we're going into the anesthetic lavas. All right? There at 90 meters, we're going out of the anesthetic lavas and you're going into. Was I didn't go on and on?
Anesthetic lavas.
Yeah.
It will be shales again.
Well, unfortunately, everything is all of the millivolt values are monotonically
Increasing. It's a smooth.
Yeah.
It's a smooth.
And over there, because again,
Where do you put a contact?
Huh?
No, that's from your borehole.
I've got this 105 meter ball.
If that's virgin data, where do you put on a
So
contact?
it's all dependent on your colour scale.
Yes, depending entirely on your colour scale, that you can apply to it. But I'm just saying is that here is the geology of this borehole that I know it's in my backyard. All right, I drilled this 110 meter borehole. It's the best thing I've ever done in my life. And I asked the director, please give me a dry borehole that's skew. Hi meneer, ons doen dit nie so. Yes.
Thanks for enjoying the talk. I just want to make one comment about the system. I think everybody has agreed that this is more of a telluric SP type system, and I think everyone came here like trying to take that angle of it. The big problem is, I think what's coming into this is the marketing of the system. That it's being marketed as an AMT receiver. When I watch the YouTube videos and stuff of the system, and we have people running around with these systems in the Cape area with the drought. And we just came back from Lambert's Bay with doing some research, and some surveys, hydrologists have used this system, spotted a borehole for one of the farmers in the region, and they drilled and they didn't get water. So I understand like all this data sets are corroborating, and a lot of this is looking also like very random data. It looks like the system's also adding a lot of values in that I'm not very confident on. I think this is more of a marketing issue, that we don't market it as an AMT system, and like I think Edgar was saying, more than telluric, sort of just that like this, it's sort of like an Excel line type thing, looking at the bumps on these graphs. We can't market it as something that's looking at depth. And I think we have to be very careful, because this is going to start giving a bad name to maybe leader tellurics. If it starts, like I think someone said, it starts giving errors, because people misinterpret the depths of the system and they give it out to clients, and they see AMT, and all they know is this is an AMT survey, and then that's the rep that other magnetic telluric systems get. I think we have to be careful on the marketing of the system.
Yeah.
Besides that, I don't want to get into the math stuff, because I don't know how you're going to process this in terms of keeping it as an AMT type system, and I agree with that should stay telluric. But I think the big problem here is marketing and educating people in geophysics. Coming from a research group where we've looked at a lot of pseudo geophysics with SU, things like this gets out in the public because it's cheap. And it becomes popular, and then it takes geophysics down when it ends up going wrong. And I think we need, as SAGA, I think Reese was saying that SAGA should look into something of quantifying these type of stuff.
Right. Sorry, can I just answer this? Can I just answer that? In that, Joseph, he pushes around this trolley and he picks up this brown paper bag. Alright? This brown paper bag is R1 million. So he goes to the BMW franchise and he buys himself an M6. Now the question is, that salesman, was he selling the M6 because he knows Joseph cannot drive correctly? Alright? That's one decision that you have to make. I just leave it there. Right? You're talking about marketing. Now, I agree wholeheartedly is that the Chinese told me it's an AMT system. Alright? And they, worldwide they go, and I'm going back tomorrow to them, well, not tomorrow I drink. Monday, I'm going to go back to them and say, look here, take the M out of this AMT. It's a telluric system, it's a pure telluric system. Please correct things over there.
And stop producing cross sections with depths like that. I think that's also.
Hey, those depth sections, alright? Those depth sections look as good as resistivity depth sections done by Griffith's inversions.
That's what? That's what?
By your Griffith. Griffith. Watch out. Ek wil julle iets wys.
Okay.
What's it?
That inversion at the bottom over there. Alright? What is that inversion based on? That inversion is based on an assumption, alright, that's a laterally the geology is laterally or vertical. All right?
Yes.
Yeah.
I agree. It's what my next question. Yes.
No. But there are so many variables that you can attach to this data. All right? And I can take the same bit of software. All right? I can take the same bit of software, and I can go and do an inversion of that data. All right? To make it look completely different. Now, which is the correct one? I'm asking you, which is the correct one? Now, hang on a second. Now,
So you're saying the other one's an inversion?
No. I am accepting that Cos had his horizontal to vertical ratio correct over here. I am of the assumption that he did 5 iterations. So at least this is not pirate software.
That's an error of like 15%.
No, but the whole thing is that but somebody who does not know, and he can go and change those filters, all right? He can change those filters, and he can change this inversion completely.
Right? That data is crap. I tell you now, if you get this blocky data, irresistability data, it's crap.
That's the
Yeah, but it's in the wrong.
Okay. I'm going to call it here. If you want to continue this discussion.
No, Sue had a question, and
I want
Vera.
I wanna.
Those of you that would like to continue this discussion,